All right, practice problems. Number one says a 6 kilogram cart is being pulled with a horizontal force of 25 newtons. If the frictional force is 15 newtons, what is the acceleration of the cart? So first thing that we are always going to do is draw a free body diagram. So I'm going to draw a little dot. You could draw a cart if you wanted to too, but I'm just going to draw a dot. And then I've got a horizontal force going 25 newtons this way. So I'm going to draw an arrow and 25 newtons. It says a frictional force of 15 newtons, so I'm going to make it just a little bit shorter than that one. So 15 newtons. And then it's saying that the mass is 6 kilograms. So really, for most of these, we're going to be needing F net is equal to ma. So if I kind of figure out what I have here, I have mass. I'm looking for acceleration. Do I have F net? Well, no, I don't yet. So what I'm going to do is I need to figure out what the result is of these two forces. So I've got 25 is positive, 15 is negative. So maybe I'll just write this over, I don't know, maybe over here. F net is going to be equal to positive 25 newtons and then plus negative 15 newtons. Or you could say minus 15 newtons, same thing. So F net is going to be equal to 10 newtons. All right, now we just plug it in. So need to solve for acceleration. So if you rearrange this formula, I've got A is equal to F net over M. So A is going to be equal to 10 newtons over 6 kilograms. So A is equal to 1.7 meters per second squared. All right, number two. A 1,200 kilogram car comes to a stop. So stop is a key word there. From a speed of 25 meters per second in 6.5 seconds. What braking force is required? So we got force involved here again. And as soon as you see that we've got things like meters per second and time and everything that we did from the last unit, remember I said acceleration is the key between those. Because really where we want to get is F net is equal to ma, right? So in the end, we're looking for the net force. I know the mass. I got to figure out the acceleration. That's what I got to do for step number one. So let's write down what we know. So just like we did last unit, I'm going to say VI is equal to 25 meters per second. I know VF is equal to 0, right? It comes to a stop. Acceleration is what I'm looking for. Oh yeah, and I know time. Yeah, so I know time is equal to 6.5 seconds. And it doesn't even say anything about distance, right? So distance is the one we don't even care about. So I would choose a formula that doesn't even have distance in it, right? So I'm going to choose a formula that has these things in it. So if we do that, the acceleration, so A, is going to be equal to VF minus VI over T. So A is going to be equal to 0 minus VI was 25 meters per second. My time was 6.5 seconds. So my acceleration is going to be negative 3.846 meters per second squared. And I just left the digits long because this isn't my final answer, right? I'm just going to leave these kind of longer than I normally would. And now, the acceleration, that just needs to go in here. So the last part, we're going to say F net is equal to mass times acceleration. So F net is going to be equal to 1,200 kilograms times negative 3.846 meters per second squared, which is equal to negative 4,615.2. So it just says what braking force is required. So really it's talking about magnitude there. So we can kind of just ignore the negative symbol. That's why there's no negative up there. And we do want it in sig digs, right? So I look it through here, and my lowest sig digs are 2, right? Both of these only have 2 sig digs. So I'm going to write this in 2 sig digs. So my final answer is F net is equal to 4.6 times 10 to the 3 newtons. All right, moving on to the next one. Okay, a 5 kilogram object experiences a 15 Newton force pulling north, a 25 Newton force pulling east, and a 20 Newton force pulling at 30 degrees east of south. This seems a lot like stuff we did in the last unit, doesn't it? What is the acceleration experienced by the object? So what we're going to have is a bunch of forces in different directions. So let's draw those out first. So I'm going to just put the 5 kilogram thing on hold. I'm going to deal with these force vectors. So I got 15 Newton force pulling north, so I'm going to draw that out and make it in red. If you guys have different colored pens and you want to stay consistent, kind of like I'm doing, I'm going to make everything going up and down red, everything going left and right. I'm going to make blue or just whatever different colors, doesn't matter. I find it helpful anyway. But, okay, so I got 15 going up. I've got 25 Newton force pulling east. Okay, so 25 newtons. And then finally, I've got 20 Newton force pulling at 30 degrees east of south. I'm going to make a little Cartesian plane to kind of get myself started here. So east is that side, south is this side. So this thing is going to be coming down this way. And this is 30 degrees. Okay, so now I have to break this thing into its components. So I'm going to have a red arrow going down. I'm going to have a blue arrow going to the right. And then you can see what we're going to do in the end here is we are going to make a new triangle out of this and figure out what the net result is. So just like we did in the last unit with displacements and velocities, now we're just doing it with forces. Okay, so we got to figure out what these red and blue arrows are. So this first one is going to be 20 newtons times cos 30 degrees. So it's going to be 17.32 newtons. The blue one is going to be 20 times cos. Oh, no, not cos. It's testing you. 20 times sine 30, which is going to be 10 even. Okay, so now what we gotta do is just make another triangle out of this. So all our red ones let's put together and our blue ones let's put together. So my red ones, so force in the y direction is gonna be positive 15 newtons plus negative 17.32 newtons. So negative 2.32 newtons. Okay. In blue, I've got Fx. It's going to be 25 newtons plus 10 newtons. So this is going to be 35 newtons. All right, we got our two sides of our new triangle, so let's make another triangle here now. So in red, I'm going to go negative 2.32, so it's going to be down. .32 newtons. And then in blue, I'm going to go to the right. This isn't really to scale. We're going to go 35 newtons. And then I'm going to have a resultant vector, or our net force. That's what we're figuring out here, right? Go in there. So that's our F net. And this is our angle. All right, now we just got to figure out, we'll go F net is going to be equal to the square root of 2.32 squared plus 35 squared. And I got a little lazy, I didn't put my units down. So I get 35.0768. I'll put all the digits. Okay, so I'm leaving that long, and then so I figured out that. I also got to figure out what the angle is, so I'll do that right now too. So the angle here, theta, is going to be equal to tan negative 1 of 10 divided by 17.32 newtons. So theta is equal to, whoops, hopefully you guys caught my mistake. I looked at the wrong triangle. I was looking back up too far. I should have been looking at this one. So to find that angle, it's going to be tan 35 newtons. So opposite side over adjacent side, 2.32 newtons. And that is 86.2. So yeah, leave it at that, 86.2 degrees. Okay. Now we know our force, right? So we're at that part, but the question said, what's the acceleration? Well, acceleration from force is an easy step. Well, all we got to do now, maybe I'll do this in green or something. F net's equal to ma, so A is equal to F net over m. So A is going to be equal to 35.0768 divided by, and that was newtons, divided by 5 kilograms. So A is going to be equal to 7.02 meters per second squared. And that's at, sorry about the cram in the writing here, 86.2 degrees. And that was east of south. Now, you might say, yeah, but the answer says 3.8 degrees south of east. Remember, those are the same thing. So that all that's talking about is it's looking at this angle. That angle there would be 3.8, and that would be south of east. I'm saying east of south. Same thing, though. They're both right. So that's my answer there. Sorry again about cramming that. All right, last one. A 130 Newton eastward force is applied for 2 seconds to a 50 kilogram object starting from rest. Underline that. On a level surface. If there is a frictional force of 50 newtons, what is the resulting displacement of the object? So again, we've got like time and displacement, and so we need the stuff from last unit, right, from kinematics. And we also need the formula F net is equal to ma. So if we're going to use that stuff from last unit, all those like displacement and v1 or vi and time, we got to figure out what the acceleration is. That's step number 1. But I guess that's step number 2. Because step number 1 is we got to figure out what the net force is. It's given us a few forces. We got that one, and we got that one. So let's draw a free body diagram. Maybe over here. So we've got an eastward force of 130 newtons. There's a frictional force of 50 newtons. So really I just need to go 130 minus 50 in the end. So F net is going to be equal to 130 newtons minus 50 newtons, or plus negative 50. $80 newtons. Okay, so we got F net, so good there. We know the mass, so let's figure out acceleration right now. So our acceleration is going to be equal to F net over m. So A is equal to 80 newtons divided by 50 kilograms. So 1.6 meters per second squared. Okay, so part one's done. Now this is a straight kinematics problem. Maybe even put a line. Oh, lost my pen. Okay, part two. Now let's write down what we know. So VI was from rest, so VI is equal to 0. VF, it doesn't really say anything about. Time was 2 seconds. We know, what else do we know? We know the acceleration we just found. Acceleration is equal to 1.6 meters per second squared. Oh, the one disappeared. And we're looking for displacement. So now we just need to use the right formula for this. So that's what we're looking for. And the right formula is going to be the one that doesn't even have VF in it, right? Because none of these have VF in it. So, distance or displacement is going to be equal to VIT plus 1/2 AT squared. And it's going to become a little easier because VI is equal to 0, so this cancels. So we just got 1/2 times acceleration of 1.6 meters per second squared times a time of 2.0 seconds squared. So my displacement is 3.2, oh, not 32, 3.2 meters. Okay, so that's going to be it for the practice problems. I'd like you guys to go ahead and do the hand-in assignment now. First part here is just figuring out what the free body diagram actually looks like. So you want to have all your forces labeled. So like in this case, we got a rock being suspended by two things. And you can see that we've got a tension force, so Ft. Maybe that's one that we didn't really talk much about, was a tension force. But it's really just, if you have a rope, you've got tension pulling up on this rock this way. You've got a force F2 going that way, and then you're going to have Fg going down. And if this thing isn't moving, I can say right off the bat too that all these must be balanced. So all the different x and y components of this thing, if I broke this up into its x and its y components, I guess I didn't draw that very well. You can see that this x component and that x component would have to be balanced. This y component and that y component would have to be balanced. Probably should use different colors. That looks confusing. Yeah, so just, you don't need to do that balancing part thing that I did there, though. You just need to label what direction the forces are actually going. Remember that things at constant velocity don't have forces on them, or if they're not moving. Well, I should say don't have forces on them. But they would be balanced forces anyway, right? There needs to be a net. If there's a net force, there's an acceleration. All right. Yeah. This one, I want you guys to try that. Most people get that wrong, but you guys are Physics 20 students now. All right, so yeah, go ahead and give those ones a try. There's quite a few there. Yeah. I'll see you guys in the next video.